This is Algebra 2 with Trig. This is the second video working through the Unit 1 review. One thing I wanted to mention back with number 11, I solved number 11 using completing the square. It was pretty messy. We had an odd number for the b value. Well, another option we could have used was quadratic formula. So quadratic formula probably could have been used for either one of these. Anytime you're working with a b value that's odd, completing the squares usually ruled out. But we've done it a few times and I completed that. Here we're working with complex numbers. We distribute our I value through, and I times I gives you I squared. And we want to turn the I squared into a -1. Collect your like terms. We like to write the imaginary number second. Here we're subtracting two binomials. We need to be sure to distribute the negative through. After you distribute the negative through, there's no need for the parentheses. It's a common mistake is to then come back and FOIL it. That gets you the wrong answer every time. -6 with those like terms. -67i with those like terms. There is no I squared. There's no -1. We're all set. Here you see that there's no addition or subtraction sign in between the binomials, so we're going to FOIL. You multiply the front, the outer, the inner, and the last. We collect our like terms. And the I squared is a -1. So we get a +16, which gives us 37 for the real numbers and 10i. Remember, your imaginary numbers go second in your answer. Here we have a quotient. We're going to take the denominator that has an I. We're going to multiply by what's called the conjugate. We multiply that to the bottom and top of the fraction. Because these are both binomials, we're going to FOIL this all together. So 3 times 5, 3 times 4, -2 times 5, -2i times 5, and -2i times 4i. That I times I gives us I squared. Gives us a +8, which is 23 plus 2i, and that's our constant. The real numbers are 23 and the imaginaries are 2i. Very similarly, here we only have to FOIL on the denominator, but we also have to multiply it to the numerator. But the FOILing is going to happen on the bottom. So we have 14 minus 21i, and on the top, 4 minus 6i plus 6i minus 9i squared. So the numerator's staying put, but the bottom's going to be 4 minus 9 times -1. And the denominator here is going to be 4 plus 9, which is 13. We want to break that up into both terms. So we have a real number, which is 14 over 13, and 21 over 13i. On our second page, we're going to write the function in vertex form. So here we notice it's a standard form. We have an x squared and we have an x. That's showing us that this is in standard form. We want to write it in vertex form. We know that vertex form has the x minus h squared plus k. To do that, we need to find that perfect square trinomial. So we need to complete the square. So we'll move our constant to the other side of the equal sign. We'll take our b value divided by 2 and square it. Gives us 64. So we're going to take this 64 and add it to both sides of the equal sign. This gives us an x minus 8 quantity squared. And on this side, we get 8. Now, if we were going to solve for x, we would take the square root of both sides. But remember, we're trying to write this in vertex form, so we just say y equals x minus 8 squared. Bring the 8 back across, which makes it a negative 8. The vertex is going to be 8, negative 8. And that's what we have. Our line of symmetry would be 8, and our minimum value would be negative 8. Again, we start out with our equation equal to 0. Add your constant to the other side. In this case, we have a leading coefficient, so we're going to pull the 3 out. And we notice that we have our b value divided by 2 and square it, which is 2 squared, which is 4. So we add 4 to inside the parentheses. We often add 4 to the other side. But notice that inside the parentheses, when we factored out the 3, that's actually going to be a 12. You've got to put the right multiple on the other side. So now we're going to have 3x plus 2 quantity squared. You got to have the square symbol. Equals 14. Subtract the 14 to the other side to write it in vertex form. And our vertex is going to be negative 2, negative 14. One way we can verify that these are right is to type it into our graphing calculator. And we can see where the graph is. We could also see what the table is. If we type our vertex form into there, we should get the same exact table, same exact graph. One fun operation is to come over, and if you hit enter when you're over here, you can make that a dark line. So graphing, you can see if it outlines the same exact line. It'll make it darker. You're pretty confident it's the same. Looking at the table, same exact numbers. So that verifies that you have the right equation. Just a way to test it. But you don't need a calculator to get your answer. Here we're going to write a quadratic in vertex form, given a vertex and a point. We have our vertex. Vertex form is x minus h squared plus k. We have our h and k and our x and y. So our y value is negative 1. We don't know the a, that's why we're trying to calculate this out. Negative 3 for the x, The h value is a -4. Got to square it. Plus 2. We add, because two negatives make a positive. Now you don't take the 2 plus the 1 to make 3. We have to subtract. So the a value is -3. If you look here, the vertex is higher than the point. So you know that it's going to be pointing downwards. Your equation is -3 x minus h, which is going to be a +4, plus 2. Again, our h and k, x and y. Our y value is 6. X value is 7. Seven minus 3 is 4. We're going to square that. Add the 2 to the other side. Square your 4 to get 16. Divided by your 16, and a equals 1/2. So our equation is going to be 1/2 x minus 3 squared minus 2. You have to have the square to make this a quadratic. Don't miss that part. Here's intercept form. In intercept form, that's going to be y equals a x minus p x minus q. So the p value will be one of the x-intercepts, and the q value is the other x-intercept. And of course our x and y. So -6 equals -1 times -6. And when we divide, we get an a value to be -1. There are two intercepts, and we have a point that's lower, so we know that it's going to be pointing downwards, which is what the a value requires because it's negative. So we have a negative x plus 3 x minus 2. You can put -1 or just a negative symbol. So we have our p and our q. So we have x minus 0. Our x value is going to be -1. Our p value is 0. Our x value is still -1. And our q value is 4. Our y value is 20. Multiply and divide. So y equals 4. X. Here we don't necessarily need parentheses around that x. And this side is going to be x minus 4. That's going to give us x-intercepts at +4 and at 0, 0. Here we're talking about the discriminant. The discriminant is b squared minus 4ac. So when we look at our quadratic, we need this to be in standard form. Now we need to move all our values of our quadratic over to the other side of the equal sign. That tells us that our A value is 1, our B value is 1, and our C value is 4. So 1 squared minus 4 times 1 times 4 gives us a negative 15. Well, negative 15 is less than 0. So think about the square root. If you take the square root of a negative number, you get an imaginary answer. So we're not going to have any real answers. We're going to have 2 imaginary solutions. Here's another standard form of an equation. We know our A value is 3, our B value is 2, and our C value is negative 1. We use our discriminant. It's 2 squared minus 4 times 3, 4AC. That's 4 minus, which is actually going to become a positive because it's a negative 4 and a negative 1 with that positive 3, so it's a positive 12. So we get 16. What 16 tells us a couple different things. For one thing, it's greater than 0, so we have 2 real solutions. And also, because it's a perfect square, this trinomial was actually factorable if we were solving for 0. Solving for x, setting it equal to 0. Next, we're going to find the zeros of the function. The zeros of the function are just like our x-intercepts, just like solutions. Just like the zeros, the roots, they're all pretty much meaning the same thing. So one way you want to look at this is, can you factor it? So here we're looking for 2 numbers that multiply to be 48 and add to be 19, which I don't think we're going to get to. We have 1 and 48, 2 and 24, and 3 and 16. There it is. There's your 19. So you know that factoring wise, 2 numbers that multiply to be 16 and add to be 19. If you're looking for the zeros, not just factoring, if you're looking for the zeros, then we are going to use the zero product property. And we get our 2 answers, negative 3 and negative 16. And here we have 8x squared plus 28x plus 12, and that can equal 0. So we could solve this using quadratic formula. We could solve this maybe by completing the square, but it doesn't look like 8 would come out at 28 very well, so that's out. We might be able to solve this by factoring, but the numbers seem kind of big. Looks like right now that 4 can come out of all of these. That makes it a little nicer. And if we look at 2 times 3, that gives us 6. That adds to be 7. That's, of course, 1 and 6. So factoring this is pretty nice. If we're solving, we really don't need what we factored out. We could divide by 4, and that makes it become just 0 on the other side. So we're going to take our 2x squared plus 7x plus 3. And 2x squared plus x plus 6x plus 3. So I'm solving this by using factor by grouping. That or guess and check would be 2 great methods. 2x plus 1. Factor out the 3, you get 2x plus 1. Notice that what's inside of the parentheses are exactly the same, and you get x plus 3, 2x plus 1. And that equals 0. We can use the zero product property to help us figure out what the value of x is. Last two questions. Find the x-intercepts of the following equation, which is the same idea as the zeros, same idea as the roots, the solutions, the x-intercepts, all the same terminology. So if we're looking for x-intercepts, want to set it equal to 0. Looks like everything's divisible by 5. We need two numbers that multiply to be negative 3, but add to be negative 4. Well, it's not going to work, not by factoring. We have negative 3 adds to be negative 4. We can get 1 and negative 3, that adds to be negative 2, but it doesn't add to be negative 4. So one way to do this is to use the quadratic formula, which is b squared plus or minus the square root of b squared, say that again, negative b plus or minus the square root of b squared minus 4ac all over 2a. That's the quadratic formula. Our b value is going to be negative 4. So we square that. The a value is 1. The c value is negative 3. That's what x equals. So first we want to put all the numbers inside the quadratic formula. (16) plus 12 over 2. So 4 plus or minus, we get 28. And we know we can take the square root of the 4 that's in there. So we have 2 root 7. And this has to be reducible on both sides of that plus or minus. So our answer is going to be 2 plus or minus square root of 7. Final one, we just have a binomial. This binomial does not have a minus in between, so there's no way that it can be a difference of two squares. So equal it to 0. A problem like this is supposed to be way easier, definitely easier than what we saw over here on the left-hand side, but many people get confused. You could use quadratic formula, but I would suggest just to pull out the 2 that's in common and the x that's in common. Leaves us with 3x plus 2. And we can use the zero product property. Divided by 2. Subtract 2. And divide by 3. Good luck.